Annual Science Forum in the National College on the topic of night parks. I really agree. The forum was founded by my teacher, Dr. Emeritus, and National College of my college.
Yes, sir.
It's an honor to be invited here. I was a student here nearly 60 years back. So I must, I think, reasonably fossilized by now. I don't know. I have very fond memories of the time I spent here. We have also some very good values and ideas, and what we are today, to some extent, is due to what happened to us when we were here as students. So thanks again, Prof.
Yes.
So I will talk about developments taking place in electric power grids. There's tremendous activity in this area. New technologies, energy technologies, materials technologies, communication and computing technologies, sensor technologies, etc. are working together to change the scene in some fundamental ways and try to solve some very difficult problems stemming from rapidly depleting energy resources, environmental issues, and the urgent need for sustainable development. Since the future of human society depends on what is happening on the energy front now, I thought I should spend some time sharing my thoughts regarding this. The developments in science and technology have been mind-boggling in the last 50 years. Maybe it was the spin-off of the effort during the Second World War, or maybe it was the paranoia and competition of the Cold War years, or perhaps it was due to the energy gathered over 100 years of industrial and scientific revolution. Perhaps it was that 100 years of energy mankind gathered during the industrial revolution and the scientific revolution, which happened around the same time. There have been explosive growth in systems of all kinds: industrial, utility, transportation, communication, financial, healthcare, etc. The list is endless. And what you see is ever-increasing complexity of technologies. What you see is size of systems growing almost like without bound. And what you see is complexity and geographical spread of systems. And there's need for better efficiency of operation, better product quality, reducing cost to consumer, reducing environmental pollution, better reliability, safety, security, etc. There are constraints of all kinds. So, recourse to modern technologies to solve problems of performance, environment, raw materials, energy, quality, cost, scale is the only way. That's the only tool we have. You have to use modern technologies. But it's precisely these developments which are taking place which has made us get into really some very big problems. So anyway, our achievements have been made possible by phenomenal developments in materials science, sensor technologies, electronics, high power and microcomputer and digital communication revolutions, automation, etc. Let's think over the past 30, 40 years. And we can now build very complex systems and integrate these systems into well-behaving, highly complex mega systems. So far as electric power is concerned, I think I used it. I'm not used this morning.
No problem. You can use it.
As I said, can you hear me?
Point.
So I'm going to be talking about the old work.
Next mic.
There has been phenomenal growth in our networks all over the world. I mean, they actually span continents. They're huge. They're incredibly large. Just to give you an idea, the P2O of Bangalore is perhaps 4,000 megawatts. This can be met by just 4 generators, each of 1,000 megawatt capacity. And if you 1,000 megawatt generator is like 1.30 million horsepower machine. That's the kind of energy that is produced. They're really huge. This is what has happened with the technological developments. Here you have the super thermal stations with these huge generators producing energy, and you can imagine the kind of coal, the amount of coal which needs to be burned, and the water requirements for cooling, for turbine operation is enormous. And even then there is hunger for power, So all the time, there is demand for more and more power. So this is what is happening. So you have these modern power systems which are large to super large hits spread across very large geographic areas. As I said, they're spread across continents that matter. And what has happened in the past 20, 25 years is there's an added thing, power trading and markets. I'll elaborate on this a little later. Earlier what we had was a vertically integrated system. The state electricity boards would generate electricity. They would take this electrical power generated to load centers, they would distribute, they would collect. Everything was done by one entity. What has happened now is that the transmission systems are kind of like highways. Anybody can get into a transmission system, if you have power to transfer, you can get into it. And then if you are applying somewhere else, they can lift the power that you have to be installed. So since power cannot be stored, it's a very complex thing. What the generator has to be immediately taken out. There has to be balance between the two. So there have to be contracts of all kinds. Bilateral, multilateral, there have to be spot markets and so on. So this has become an extremely complex thing. The advantage is that all kinds of power producers can get access to the transmission system and the distribution system. And there are benefits because of competition to the consumer. So this is what has happened, power trading in markets. And the problem here, of course, is the random complexity, enormous complexity, because unless you have information, I entered into contract with I have a big factory, and I entered into contract with the power producer, and precisely, every 15 minutes, how much of power I'm going to lift, and so on. And the power producer says, okay, as per your demand, I'm going to produce that amount of power. And somebody has to see whether this is happening as per the agreements. Because if it's not happening as per the agreements, there are big problems in our system because energy cannot be stored. So voltage will increase gradually, the frequency will increase, all kinds of things happen, and you will have to take measures of protection. So you have to take recourse to information technology and advance it. So this is the thing. This is what has happened. So there are major worries. One of the things is availability of non-renewable energy sources, fossil fuels. I mean, mankind is really, going on with expansion and all kinds of things, thinking that there's never going to be a shortage of them, but we are in really big trouble. We have to harness renewable energy sources. It's not easy. We have to think of all kinds of energy sources, the solar, or hydro in remote places, wind, all kinds of biomass, and so on. There is worry about emission of greenhouse gases. There is worry about reliability and quality. Morning, these days, you demand that you must get quality power, highly reliable, and so on, at least in the Western world. And that has to be assured. It's not an easy thing. And since there's a lot of embedded computation which takes place all over, and since there is the data or the information network, and since there are connections to the internet and so on, this particular thing, cybersecurity has become a big problem. People can cripple these networks, and that's happening as a matter of fact. It's a very interesting study, kind of things that have happened in the past, and the steps that are taken to protect. And then failure and disaster management, like when there's a blackout. You try to prevent blackouts as far as possible. One of the recent blackouts, I think 2/3 of India was blacked out. One of the biggest ever disaster in this area of electric power systems all over the world. With all our expertise, studies and everything, people prevent it. The point is, when that kind of thing happens, when a huge part of the country comes to a standstill, what do you do? How do you put the things back again together? Unfortunately, these are synchronous networks. All these generators are synchronous machines, in the sense that they are tied to each other electrically. One machine, the frequency is the same all over. It's in phase block, if you know what I mean. If the speed of one machine changes with respect to other machines, there will be disaster. Ultimately, it cools down, the huge current flow in the network, and the generator has to be removed. So managing synchronous networks is not easy. It's a difficult problem. So failure, disaster management. When ultimately things are happening, the system has come crashing down, there's a blackout. How do you put it back together? One generator after another, checking, cross-checking, making sure that everything is okay, and compoundedly you have to take care of the loads. Not an easy thing. So these are all very big worries. And for many of them, they are taking recourse to large-scale use of information and communication technologies. You have communication taking place on a grand scale, communication, and then you study everything, and then you say, if you do like this, it will be okay, and so on. So this is where, when you have built an extremely complex system, if you want to manage it, you cannot do it the old way, manual. It has to be automatic. And that implies computers, that implies communication, that implies automation, and so on. So big areas. So this is where you have this development taking place, tremendous activity in the development of smart grids, using computation, computers, and communication, and all kinds of other things. You build this smartness into the system. And these are huge systems that, as a matter of fact, spanning countries. So you know what the problem is. You know how complex things are. Okay. Now, I think we'll step back a little bit at this point. I want to go back to 1452. Gutenberg's moving type printing machine. The people who said that because all these things that are happening now, if you really see it's because of what happened in 1452, Gutenberg is moving type printing machine. Their knowledge was confined to minuscule, special groups of people, religious or whatever, before the printing happened. And with this very simple, innocent looking kind of development, what happened was it liberated mankind. It democratized education. Education was confined to small groups, now was available to others because we trade books, we distribute books in large numbers. And that changed everything. So it gave a kind of capability to mankind that we have never tasted ever before. So, and one thing led to another, schools got established, colleges got established. In the beginning, maybe it was religious books, later on it was books to inform, all kinds of things to entertain, perhaps, and so on and so forth. So, this is what happened. So, this led to the first industrial revolution, late 18th and early part of 19th century. And the first revolution was all about steam engines, coal. It was all about coal, all about steam engines, textiles, railways, steam engine factories, and so on. And it got a huge change in society at that time, at least in those parts of the world that it happened. And the second industrial revolution was in the 19th and 20th centuries, and it was driven by, again, energy figures in a very fundamental way. What I want to stress is, look, ultimately it's all energy and energy research. And we have a problem on the energy front, we have big problems. The second industrial revolution, because in the 19th and 20th centuries, both petroleum, chemical, steel, electrical power, IC engines, communication, transportation, mass production, urbanization, etc. And if you really look at what happened during that period, maybe 100 years or so, there had never been such energy, such a display of creativity, such levels of activity, such a scale of achievement, and yes, such a scale of exploitation of nature at any time earlier in human history. Energy and its lasting use were central to industrial revolutions. They indeed are even today. So, and what energy has? How did that happen? Because standard of living went up. People were not dying suddenly. Healthcare and so on, food availability, so population matter, rapid urbanization, same time, because of these technologies, environmental degradation, pollution, the problem with water, air, food, resource crunch, mass destruction capability because of the world loss, whatever, etc. The serious part, right? Is not good. So one mankind will need all its energy, all its knowledge, all its ingenuity, sustain our hard work and cooperative spirit and wisdom to find solutions. Now the third industrial revolution is on. At least that's what many people say. Started in 1970s. 1950, the transistor, and so on 1970s, the 1960s, it was the integrated the chip, integrated circuits, and so on. And so 1970s, communication and computing revolution started. And there's no area of science, technology, industry, commerce, management, and all it's not touched by in deep and fundamental ways. ICT. There are other developments too, materials, nanotech, bio, etc. So the thing So let's get back to electrical power. So as I said, these are very large complex systems, complex operation, complex dynamics, etc. etc. I work very dense interconnected remote power sources. And generation is fossil fuel, thermal, hydro, nuclear, wind, solar, biomass, etc. The main energy comes from fossil fuels, coal and petroleum based, natural gas. These are the main things. And they are not renewable. One day they will evolve in the future. And since everything in modern life depends on these things, the petroleum, plastic, drugs, pharmaceuticals, fertilizer, maybe it is dependent on that. So it is not the only live, that kind of thing. So then, this is the thing. So we have been ever increased in the field of instrumentation, automation, communication technology to meet the needs of technical and market operations. But where will this lead? So as India is concerned, we have 5 regional electricity boards spanning the whole country. I think some of these things I'll skip because I'm getting into a place where there are some technical things. So, what we of course want is least cost production, transmission, distribution, least damage to environment, good quality and reliable supply, promote of welfare to people, rural supply to remote places and so on, fair and reasonable tariff structures and so on. So this was the way it was before the political organization, the power producer, the same as the person, the entity which transmits, takes power to load centers and then distributes and so only one like state electricity boards. So during that time, this way they did things, and nowadays things have changed somewhat because of deregulation as they call it. So hopefully, we'll still be able to do all these things. Okay. Now, these power systems, normal operation is the following. There's a demand, you have load connected, all kinds of big cities, factories, railways, whatever, loads all over the place. So to meet the demand of these loads, there has to be generation, equal to the demand. And generation has to be slightly more because there are losses in the network. So you have to meet whatever load demand is there, plus whatever losses there, plus that has to be generation. All of that, it has to be there. Not just that. When you do this, all quantities must be within limits. For example, voltages. You transmit electrical power at generally in India, the main transmission voltage is 400,000 volts. Now, you allow this voltage to go up or down by a small amount. All the time, the voltage has to be maintained with time, no matter what. So there are all kinds of constraints. There are constraints of the amount of current that can flow on the transmission lines, and so on. So constraints on phase angles and various kinds of constraints. So you have to observe all these constraints all the time. Now, supposing the system is observing all the constraints and it is operating satisfactorily, but supposing some contingency takes place, like there's a lightning strike. When there's a lightning strike, maybe one of these lines which is carrying a huge amount of power, they trip, that open out because there's big voltage on them because of lightning strike. There are things which protect the line, they open the line. Now, under normal condition, even when this happens, the system must be okay. So only then we say that it is normal. Now, in alert condition, still everything is okay, all the values are within limits and so on, but if a contingency takes place, like a lightning strike or something, the system will collapse. Then it's called an alert state. And they have to ahead of time work out strategies. If this happens, what should I do? If that happens, what should I do? And in order to work out these strategies, you must know what would happen. For example, if a particular line were to open out, you must know what exactly happens because of that to the system under the present conditions. So what they do is huge calculations, computer-based computations, the huge calculations which are done. So you have a large number of contingencies because any one of many things can happen. So for each contingency, you make a simulation study and find out when this contingency takes place, what would happen. And knowing that, you try to figure out what should you do now at the present time in order to avoid the bad effects of this contingency. So you can see the amount of computation in near real time which has to be done. And this is happening all the time. In centers, energy management centers, this contingency analysis, as they say, is done. Ongoing thing. Otherwise, you will not be able to handle it. So you have all these things, alert state, emergency, in extremis. In extremis, you have not been able to do anything, the system has collapsed. And then you must have a strategy to put it back together again. And that is the frustrating thing. In extremis, there's a backup. The system has collapsed. So all of these things have to be taken care of. And how do you take care of them? Through control, of course. And what kind of control do you have? You will not get into these technical things. But I just want to give you a feeling for what goes on. In these management centers, energy management centers, under normal conditions and abnormal conditions as well. So we'll skip these things because it's technical. And as I said, security monitoring is very important. Emergency control is very important. Strategies for doing that and so on. And supervisory control all the time. So that's very important and so on. So, and various things. So we'll skip this. Maybe just this. You have to have reserves. Supposing a contingency takes place, and in order to avoid disaster, supposing additional power should be available to you, just suppose, and it has to be supplied immediately. So there are certain generators which are not supplying any power, but they are kept in readiness. So it is called spinning reserve, and so on. So you have to plan for everything, and you have to have. So, okay. Then the deregulation, which has brought in tremendous complex norms in India, to that extent, though we do have some electrical power trade and so on, but not as it has happened in the West, where it's on very large scale. So these generators, they may belong to anybody. So let's say I want to set up a power plant, produce power. I must be able to dump that power into the system. I must have laws which enable me, permit me to do that. In other words, these transmission lines are like highways, and I'm transporting power. And I'm transporting power for my client who may be 1,000 kilometers away. So, and we have entered into an agreement, as I said earlier, contracts and so on. Everything has to be as per that. And so you have free generators, free access to transmission systems, wheeling rights, in other words, transporting power to wherever it is required. If there are the systems in between, for example, like Our generation is, let's say, in Orissa, and the work center is in Bangalore, and they have entered into a contract. The power has to flow to intermediate regions. You must allow that to happen. So legislation has to be there. So this is called bidding. And intermediate systems must permit this flow of power. Power as a traded commodity, contracts, spot markets, wholesale, retail, all kinds of things. And so the point is, how do you manage the system under these conditions? Whose responsibility is it? And how do you keep track of things, metering, calculating, billing, settlements? Because any contract is a legal thing. So all this. So there's huge need for information technology, huge need for information and for communication. And using this, whatever you have measured, whatever information you have gathered, whatever computations you have made, you must be able to communicate, and you must be able to act on it. So you have the power network. Along with that, you have this information network too. So it's a cyber-physical system that you have these days. Now, the main thing is about smart grids. It's a big revolution which is happening. What they need are smart grids. These are the old grids, really, but you have brought in a lot of intelligence, a lot of computation, communication, and a lot of other technology, energy technologies, and so on, in order to do things in a much better way. So let's see what it is. Now, what do we mean by smartness? So, for example, if you're talking about a sensor system, something which measures a quantity and transmits the quantity to another place, in an industrial context. Smartness may mean that it must be able to self-test and say that I'm all right. Whatever information I'm transmitting, the measured information is okay, you can take it. It is, so because I'm in a healthy state. So self-test is important. It must have communication capability. So in other words, it's a part of a system, and it must be able to communicate wherever required. Self-healing, if there's a fault, if there's a fault in the system, it should be able to set right, heal itself. So energy saving, optimal operation, plug and play. It must be very simple. I just plug a sensor into the system. It announces to the system that it is there. It gives all the details. It gets integrated all automatically, and it starts functioning. So this is called plug and play, and so on. So smartness definition for highly complex systems such as modern processes can also be articulated at a broad level. So smart grids are such grids really. So this is interesting. This was way back in 2005, and the North American electric power system is in the early days of a profound change. This is from that paper from Global Environmental Fund Center for Smart Energy, white paper, the Emerging Smart Grid, October 2005. This is what was said. The electromechanical grid of the previous century is being transformed by computers and electronics into a smart grid. The same technologies that revolutionized computing, remade telecommunications, and created the internet, computers, electronics, and advanced materials are now reshaping the electrical power infrastructure. So, very large scale things happening in the. Okay. So, the core technologies here are distributed intelligence, sensors, controls, data networks, and communication. So, you have the power network, and you also have together with it data network. Advanced software and systems, power electronics, central and distributed generation, virtual aggregation of generators and loads for system management. So this may not make sense to you. Let me just give an example. Suppose we have decided, as a matter of fact, that's what is happening in places like California, that I can generate my own electricity, maybe photovoltaic, like you have rooftop water heating systems. You can have photovoltaic generation or whatever other way of generating electricity, whatever you require, and you have electronics to go with it. In other words, the power which is generated is converted into a form, electrical power, so that you can use it. Like you have a continuous 230 volts, 50 hertz, 50 cycles per second, that kind of power. If you have additional power, you must be able to push it into the grid, and you must be paid for it. If your power is deficient, you must be able to draw power from the grid, and you must pay for it, of course. So, this has to happen. Now, suppose there are, let's say, 1 million people who are generating power. Other problems in dumping their extra power into the network, etc. Now the network people say, now can you give me an idea of how much power I can get and at what time, how reliable it is? Because there are contracts. You have to work out contracts. And if there is uncertainty about this, if there is no clarity, then it's difficult. So if there are shortages, or if there is, then somebody has to supply the excess power that is required. So you must have power plants kept ready for doing this. But all kinds of management issues. So how do you do it? Now, let me say, from a central place, can I have a control over each of your power generating plants in your home? Can I control? Because if I have the ability to control, then things will be simpler. So this is what I meant here, virtual aggregation of generators. So in a particular locality, I will put all those small generating units together. So far as the operators are concerned, the system operators are concerned, it is one single unit. There will be 10,000, 15,000 households, and they will all be controlled as if they are one entity together. So this is what I meant, virtual aggregation of generators. And grid components connected by both electrical and data networks. So let's say that you have a washing machine in your house. Now this washing machine is an intelligent washing machine. It has the ability to communicate with the system. Now the system tells the washing machine, and we are trying to switch this on. We want to switch it on now, because if you use it now, they are going to get a lot of money. There is congestion. There is heavy demand on energy. There is congestions in several lines. If you try to take power, you will have to pay a lot of money. Are you able to do that? Now you have to do a program, because it's all computer, there's no human intervention or anything. The computer works things out. The computer says, well, I can maybe, it's okay, I can wash in the night. So what would the tariff be at that time? And let's suppose it's dynamic tariff. In other words, it's not free kind of, the tariff depends on the situation. And it's worked out dynamically. So the system says, I don't know what the tariff will be in the night. However, from my past experience, the tariff is something like this. It will be much, much cheaper. The cost of electricity probably is going to be 1/4 of what it is now. Would you want to wait? You have programmed your computer in the washing machine to say that yes, wait. Automatic. So for these things to happen, every power consuming entity must be intelligent. It must be able to talk to the system, and it must be able to figure out what is the best operation. And this is best minded from the point of view of the consumer, it is best from the point of view of the power supply. So it is what we call the win-win kind of situation. Can you enable these things. So this is what the spirit of smart grid is. That's the direction. And then you say, I don't want to, when you say communication, I don't want to have separate lines for communication, digital communication. I don't want that. I don't want to use Wi-Fi. I don't want to have, cables. Can I not use the electrical wire? It's already there. Power line communication, can I not do that? There's a lot of development taking place there. So you don't have to have any other system for communication. You just plug the thing into the socket and automatically communication takes place. This is the direction in which changes are taking place. Bidirectional power flows, because you are power producers, you consume power, as well as you sell power, so power flows can be bidirectional. So the several key characteristics of smart grid: self-healing. The grid must be able to rapidly detect, analyze, respond and restore from perturbations. Blackout should not happen. And this has to be automatic. You have to have equipment to do this, you have to have computations you should figure out. So empower and incorporate the consumer. As I said, the intelligent washing machine deciding. This is empowerment of the consumer. The ability to incorporate consumer equipment and behavior in the designing operation of the grid. Tolerant of attack, a grid that mitigates and stands resilient to physical and cyber security attacks. Provides power quality needed by the 20th century users. A grid that provides quality of power consistent with consumer and industry needs. And this is very important. Accommodates a wide variety of generation options. So distributed generation, all kinds of generation options. So, and fully enables measuring electric markets, optimizes access and so on. So there are basic characteristics of the smart grid. So this is an act actually of the United States. This act is to empower the industry and make things happen. So it essentially is along the lines that I just now read. And then microgrids, like let's say this area, residential area of Bangalore, can it form a microgrid? In other words, you can take care of your needs to a very large extent because you have capability to generate power. Whatever it is, you will not get into that. Suppose, just suppose, you have capability. And if you have extra power, this particular microgrid of personal grid, you'll be able to sell this grid to the best power, whatever. And then if there's shortage, they will take. The point is, if there's a big problem with the grid, immediately this microgrid should be able to separate out and be on its own. So it can have strategies for doing that. It may switch off many types of loads, and essential loads only will be there, but it will be intact. So in other words, it will operate as if it is a UPS, uninterrupted power supply. Even though the grid is disconnected from this whole area of this microgrid, it will stay healthy. So of course, with reduced all the essential loads will be supplied. So this is what smart technologies can do. There are all kinds of challenges. Since I'm running out of time, I will skip these things. It's not easy with all the things that you have, power of computation, communication, sensor technologies, and energy technologies. Still, it's difficult. Slowly there's a change towards using electrical vehicles, electrical powered vehicles, hybrid vehicles, and vehicles which use, and they have to be charged. So how do you do that? Maybe during the night time when the load of the system is not heavy. And since each of these vehicles has a battery in it, maybe it can enter into trade. You have need for power, and your car is not doing anything, it's sitting in the garage. You can sell some power, make some money, if it's renewable. So all these things are happening really. So okay, I think so the main thing is how to manage all these things in the deregulated environment. Because remember that there's power trade, there are contracts. So unknowns are make it difficult when you have contracts. When you have, let's say, significant amount of wind generation. And then you think, you see the forecast, the wind flow, the historical data, all kinds of things, and ultimately you enter into a contract. And during that time, if it is not going well, then you have to have a agreement with somebody, If such a thing happens, you burn fossil fuel, can you generate that amount of electrical power and dump it into the system because my clients are entering into a contract. That fellow says, okay, I will do it, but I have to keep myself ready with this equipment. And I'm really not sure whether you will give me a chance to use this equipment because it all depends on the wind. So you have to pay a lot of money. So these issues come into picture. So how to manage all these things in the deregulated environment? Very tough job. So I think I'm giving you a feeling for the complexities. But the main thing is that we have to go away from too much of dependence on fossil fuels. We have to explore all kinds of other types of generations. And those generations are not going to be, they're small. It's a huge number of them, but each one is able to generate only a small amount of power. So you have to put it all together and manage things. How do you do it? So, okay. I think it's, there's you might have heard of him, this person, Jeremy Rifkin. A very influential person. He's an economist, a social theorist, writer, public speaker, political advisor, activist, highly influential, and government's construction. So he has this best-selling book, The Third Industrial Revolution: How Natural Power is Transforming Energy, the Economy, and the World. And what he's saying is some of the things that I mentioned. He says you have to shift to renewable energy. You just don't have non-renewable energy sources. They will not last for a long time, maybe another 50 years. There's going to be a big disaster for mankind. And so we have to shift. And the shifting will be enabled by smart grid technologies. And what he says is buildings must act as power plants. Every little bit of energy that falls on the building, solar energy, you must be able to convert it to electricity. So, when you read what he has written, you feel that still, it's kind of woolly, it's not very clear and so on. He's still not down to earth. And he says, hydrogen and other storage technologies are to be developed. It's essential. If you have extra, you must convert it to hydrogen. And then this hydrogen, whenever it is required, like in my house, I have accumulated some extra power. I have converted all into hydrogen. He says it's possible, not spending too much money, and I store it in the house. And then my neighbor says, internet, I have need for power, There's a function in my house. Do you have it? I say, I have just the amount for you. And this hydrogen, I push it to a fuel cell, generate electricity, dump it into the system, and he picks up that energy. You know what I mean? So he says, this is like, the internet. He says it's power internet. That's what he calls it. So that's his vision. because I don't know to what extent it will work, but using internet technology to transform the power grid, business and households to produce their own energy and share it with one another, transform transport fleet to electrical plug and hydrogen fuel cell vehicles. Plugging can also carry electricity. Like I said, any vehicle which has a battery in it, store electricity, and it can enter into, you are not going to use your vehicle for the next 1 day, and somebody says, I'll pay whatever you want, give me some electricity, you release that electricity. Or, this all kind of should happen more or less automatically. So all these things are possible. And he says, these 5 pillars, this is one of them. Okay? And then hydrogen fuel cell vehicles. Additionally, democratization of manufacturing through 3D printing. We will have to get into some discussion regarding what exactly it is and so on. It's a very interesting problem. So the thing is, this person is so influential. European Union has discussed and is consulted by all these governments, Germany, Netherlands, and various other, and they have all endorsed what he says. They say, this is the direction we go. This is the direction we go. Otherwise, there is no future for mankind. Fossil fuels are broken in. This is the direction. But when you read all these things, you ask, will it really work? We are so power hungry. We are so powerful. Humanity has become. Once I just sat with a friend, armchair, he said, let's get an idea of how much of oil is pumped out. I mean, this data is easily available. Amount of energy consumed by mankind is mind-boggling. But just as an exercise, so we just sat and said, how much petrol is used? Say in the United States, we said, okay, petrol is used there. Let's talk about cars. How many cars are there? It depends on households. How many households are there? It depends on the population. What's the population? 200 million. Okay. So how many households? Divided by 5 or 4 or whatever. So many households. Each household on the average, how many cars do they have? Maybe 1.5. Okay, 1.5. Now each car per day, what distance does it run? You make some calculations, some guesswork. And ultimately, you say how many gallons are required, how many liters are required. And then 200 million, put it together. Now, to produce that amount of petrol, how much petroleum should be pumped out? Now, it is not just that. We have all the buses and the lorries and trucks and all kinds of other commercial vehicles. We have ships, we have aeroplanes, and in huge cities, like city of Chicago, the whole city is heated. All the buildings are heated in winter. In summer, air conditioning, where does it come from? It's all from, so if you put it on together and see the amount of energy, or fossil, petroleum, if you like, that is pumped around, can this be so forever? Or how long? It appears to me that the attitude of mankind now is who cares? That the going is who cares? Who cares? But it is scary because you ask also this kind of question. Supposing it is not there, what will happen? Supposing petroleum is not there. You say, okay, no cars will fly. Is that all? You start talking about other things that petroleum gives you. And then you find the whole civilization collapse. Nothing less than that. That's why this Rifkin, whatever he's saying is, these people, the big governments are listening to him carefully. He's become a bestseller. He's a very powerful speaker. You have his presentations on the internet, literally. But will this really work? I don't know. I don't think so. My gut feeling is that. So, okay, now, at this point, maybe this is a sober note. Another 5 minutes, I'll end. Sober note. Are there limits to growth? Only endless, Always, see, you say fossil fuels do not be available. Nuclear, no. Not after Chernobyl, not after what happened in Japan, not after Vietnam. No, it cannot happen. Then solar, okay, solar. How much? How much? Wind, how much? Hydro. Those places are all far away, up in the mountains. You have to somehow, so when you do like this, you find that. So in 1968, the Club of Rome was founded as a think tank, among other things. It was formed by a group of scientists, economists, business people, high-level public servants, heads of states, and former heads of state, all from 5 continents. This group wanted to address the larger questions confronting the global society because existing ways were too narrow and governments too compartmentalized. They desired to act as catalysts to stimulate public debate. And the main person who motivated was an Italian businessman. And so it's a very serious kind of people. So what they did was, they asked MIT, Professor Forrester was, to examine what would happen if people continue to consume world resources the way they were doing. The study was by modeling and simulation, because the whole global system has to be studied. They took 5 state variables. It was a highly nonlinear system. They actually, they have to say this model is all right. In other words, the results that this model is going to give will be all right. It is telling the truth, to some extent. So all that was done. People agreed, okay, this is a true model, but it's all right. It will give you the essence of things and so on. It will not too true. It's a very famous study. So the study was by modeling and simulation. The study became the basis for the book published in 1972 called Limits to Growth. The book shook the world. It sold 12 million copies in 37 languages. Why did it shake the world? The book warned that if the consumption patterns and population growth went unchecked, the earth would strike its limits to sustain within a century. In other words, just a century was available from that 1960, whatever, 1970s. So, 1 century later, so the book warned of incredibly grim prospect for mankind in the near future. My comment is, 100 places, nothing in human history. Homo sapiens, this particular species has been around for 50,000 years, 100,000 years, I don't know, not more than that. I think the species evolved. So, and then we are going to wipe out everything because of progress, because of industrialization, because of exploiting nature, and so on. And nature gets back. So this is what they said. 100 years is nothing in human history. That is what I said. It was difficult to swallow the message that there would be total collapse, an apocalypse, if you like, in the span of 4 to 5 generations. Many people made fun of this study. They said they actually labeled them as doomsday experts. But you cannot visualize that there is limit. There are limits to growth. You cannot go on and on consuming and developing the way you are doing. So, okay, this is a great prospect. And I think at this point I had to ask myself, so how should I take this? I'm a technical person. I know what things are possible, what is happening, and so on. Very exciting things. But then you have this dream prospect. So I said I'll just make this statement and end my talk. Technology alone can solve all our problems. But knowledge, wisdom, and courage. Yes, courage. What do you mean by courage? You're not going to have it. So can you learn to live some other way? In a simpler way, maybe. Not simpler way. Then you and your people will live decent lives, but you will not exploit nature and get into. So I don't know. But knowledge, wisdom, and perhaps get help from them.